So from here onwards, we will start thinking about gravity not as two objects pulling each other, but thinking of each object with mass, creating a field around it. So what is this field? See, the word field, electrical field, magnetic field, the word field is nothing but, say, a three-dimensional space wherein you get to feel non-contact force. So field is a region wherein you get to feel non-contact force. So if it's gravitational field, we are looking at gravitational force. The cause is gravity. The cause is mass. So that's what we're looking at. We are looking at gravitational field. So basic idea of the word field is that it's the region of space where an object with certain criteria experience force. It can be a pull or a push. So specific to gravitational field, the basic idea is that every object with mass has gravitational field around it. It's like an invisible bubble that extends outward in all directions. Anything with mass that enters this bubble feels a pull towards the center of the object. Since it's a pull force only, since it's an attracting force only, gravity, so this statement is valid. So the official definition of gravitational field is that the gravitational field at a point in space equals the gravitational force exerted by a test particle placed at that point divided by the mass of the test particle. So this is a small note. The test particle are generally taken to be very small so that they don't disturb the original gravitational field. So this idea, all of this idea will be used when you're studying magnetic field, electrical field and all of that. So you need to carry forward these ideas, okay? So what we are telling is we are defining. See, if I want to study something, say this object has some mass and it is, sorry, just a second. It is producing a gravitational field around it, something like this. Agree? So if I want to study about this gravitational field, what do? I need someone inside it. If I want to study something, I need to analyze it. So in this case, I need to be part of the field. So I can say set up my station over here. Right? So in this case, my station is a test particle. So we call it as test particle of mass m. So now this is feeling a force of F. So gravitational field, which is represented with E and stuff. So, or let me just go with gravitational field. So gravitational field can be defined as the force that this test particle feels, okay, force felt by the test particle divided by the mass of the test particle. Divided by the mass of the test particle, as simple as that. So basically, indirectly, we're talking about what unit mass, what amount of force does a unit mass feel over here? What amount of force a unit mass feels over here, here, and so on and so forth. So that is how you study gravitational field. Okay. So of course, if you don't have unit mass per se, you can take any mass, study how much force it's exerting, and then divide it. So you'll get, end of it, force per unit mass. Force per unit mass. So that's your gravitational field. So there's a small statement that mass m of t, so your test mass. See, even test mass, even though it's just a dot, it also creates a gravitational field of its own. You guys agree? So it also creates a gravitational field of its own. So we have to be very careful that this field is not that big. It does not disturb the original field, right? It's like we are contaminating it. So what we try to do is we will try to see to that the intensity or the strength is almost negligible. It's It's actually extends till infinity. I can't reduce the range, but I can see to that the intensity is not that great, as in it's not that strong basically. So technically we are taking a mass which is very low. So that's the whole idea. So that's one point we are doing over here, that test mass must be very small so that it does not disturb the original gravitational field. Like if I take an ant to study the gravitational field of the Mars, for example. So ant mass is nowhere compared to Mars's pull or Mars's mass. So technically the ant will feel the pull, is it not? So that's how we can study a field, taking a test mass. And technically the test mass has to be as small as possible. The presence of test particle is not necessary for a field to exist. See, it's like this. If I have this charge or no. So that statement is this. If I take this charge out, will the field still exist? Yes, it doesn't matter. So test particle is only for us to study. So field exists even without that. In essence, we are describing the effect that any object has on the empty space around itself in terms of the force that would be present if a second object were somewhere in that space. So what we are trying to tell is, gravitational field, or the idea of gravity, it's not because of two objects being close to each other or far away from each other or existing with masses. Even if you have a single object with mass, it will disturb the field around it, region around it, right? Even without the existence of other mass. So till now we have been talking about gravitational force and all of that in terms of two objects being present, they pull each other. No, it's not so. Gravity and the field will exist even though there is no second object. So it will have its effect on the empty space around it itself, that is, in terms of the force. So it will always exist even though we don't have the second mass. It sounds a bit philosophical, but that's the idea. Okay, yeah, that's the official idea. You just need to know it. Again guys, the idea of gravitational field or field, the same thing will be reflected in your magnetic field, electrical field as well. So don't miss anything from this chapter. If you learn this chapter, it's like you have learned 2-3 chapters put together.